Hi guys, this is Team 5 for Embedded System Design, Summer 2020 with Dr. Plasman. Remus Li, and I'm doing the camera system part.
My name is Nelson Downs, and I have done the navigation system in the GUI.
Hello, I'm Lingze Zeng. My job is setting up the robotic arm.
My name is Dixuan Wang. I'm in charge of the rover control system.
For our project this summer, we have created a game similar to the popular board game Battleship, which we have coined Hospital Ship. The game takes place on a 10 by 10 grid where each square either contains a ship or is just the sea. The ship squares are grouped in rectangular sections of varying sizes to represent different sized ships. The goal is to try and guess which squares have ships and deliver medicine, represented by foam blocks, to as many ship squares as possible. There's only a limited supply of medicine, however, so the player must make educated guesses based on the feedback received from previous moves and knowledge that ship squares usually are connected to other ship squares. We implemented our game by constructing a 10-foot by 10-foot grid, each cell being 1 square foot, on a hardwood floor. Squares that contain ships are colored using red construction paper. A robotic arm is used to pick up foam blocks that are detected by a camera and load them onto a tri-rover. The user selects coordinates from a GUI, and the rover navigates the field to the coordinate and drops off the medicine. It avoids the squares that already have foam blocks with the use of a navigation system. The navigation system makes use of 3 task threads: the path task, the I2C task, and the MQTT receive task. The path task is responsible for calculating the shortest path to the coordinate selected on the GUI, and does so using a breadth-first search algorithm and a linked list. The breadth-first search works by starting from the home position, the coordinate the rover is initially placed, and adding all adjacent cells which are not obstacles and haven't been visited yet to a queue. It then loops along this queue with the same procedure until the destination coordinate is found. Each coordinate processed in this manner keeps a pointer to the previous coordinate, so the path can be traversed after the destination coordinate is found, which is a linked list. This task also is responsible for directing the rover to the destination coordinate by sending it messages over MQTT, which contain directions similar to how a GPS driver directs a driver: turn left, right, etc. It also lets the robotic arm know when the rover is ready to be loaded with another foam block. The MQTT receive task is responsible for receiving MQTT messages from the other systems and sending them as queue messages to the path task for processing. The path task uses these messages to determine when the robotic arm and the rover systems have finished moving and are ready for their next move. The coordinate from the GUI is also received in the path task in this manner. The I2C task is responsible for reading RGB color values from a TCS 34725 sensor over I2C. It reads the values periodically by using a timer. The timer is set at a period of 308 milliseconds, twice the integration time for the color sensor, in order to avoid sampling issues. A callback function is specified for the timer, which is a function designated to run at every time a specific event occurs. In this case, every time the timer interrupt occurs. This function sends a message to the I2C task through the I2C message queue, telling it that it is time to take another color reading through the sensor. The I2C task receives this message. When the I2C task receives this message, it conducts I2C transactions with the sensor to determine the RGB values read. The I2C task waits for the publish message from the path task, which occurs when the rover reaches its destination. When this message is received, it detects whether the color represents a ship square or not and publishes it to the GUI. The GUI then shows the user what was detected. The GUI is a web application written in Node.js. It uses the Express.js framework to serve the web pages which make up the GUI, and the MQTT NPM module to receive and broadcast messages over MQTT to the embedded systems. When MQTT messages come through, the server parses and stores the data in memory. It also computes statistics based on the sequence numbers added to each MQTT message. The actual GUI pages are statically served with Express.js, which means they are simply HTML, CSS, and JS files transferred to the browser once per HTTP request. Endpoints are set up with the Express.js, which send the stored data, such as the state of the grid, statistics data, and sensor data, over HTTP requests. The web pages contain timers which run multiple times per second and pull these endpoints and update the GUI, effectively showing the data in real time. This is the data channel. We can see that the data is represented on the GUI in real time. I am moving the color sensor around on the ground, and you can see the colors are changing. If I move it over a red square, we can see the colors change there. So the color is represented in a human readable format as well as the RGB values, so that you can easily see what color is coming through the sensor. So like even if I held it over the blue of the background here, you can see that it changes there. So that is how the data channel works, and all of this data is coming through MQTT multiple times per second and is displayed on the GUI.
The camera connects to the TI board via SPI interface, and it is trained in OpenMV IDE. It can detect the color and return a rounding box of the object and calculate the distance. So there are two queues. One is the timer queue and the other one is the message queue. So if a value is red in the timer queue in the SPI thread, it will start a transfer with 4 times per second. Then it will push to the message queue and publish on the MQTT. In our case, we use the mqtt.eclipse.org as a public broker, where we can publish and subscribe to the topics that are unique to the Team 5.
Robotic arm task diagram. As we can see from the diagram, everything begins from MQTT, which will send navigation system message and camera sensor message to the queue. With a message from the queue, a thread will process camera data, and when navigation send me the signal that arm should work, camera processing thread will send message to my state machine, which is used to modify each motor PWM in the arm. According to the camera, the arm is able to know the direction of cubes and distance from arm to cubes, so that the arm will move to the direction of the cubes and grab it. After grabbing the cube, the arm will begin to test whether the distance between arm and cube is the same. If the distance is the same, it means I grabbed the cube successfully, but if not, it will begin grab action one more time. After all stuff above are done, the arm will turn to rover and reload the cube, and then it will send message to MQTT to say my work is done.
Here's the rover task diagram. Everything starts with MQTT thread. It reads messages from the navigation system and then write a navigation message to the rover control queue. Then the rover control thread reads from this queue. If the message is a navigation message, it will use UR to set the rover's motion. After doing so, it gives a status message which tells where the rover is moving to the rover status queue. In order to keep this rover moving straight and it will stop once it arrives, we use a PID control. P means proportional, I means integrational, D means differential. In this case, we are only using proportional and integrational. To use this thread, we have to know where the rover is moving because in different mode, the PID thread is different. So here, it reads from the rover status queue, and we have this status message here. So it gets its status message, it will set the PID mode, then read again. The other message is the encoder message. Encoder message is given by SPI thread. It reads from a timer callback function every 200 milliseconds. It will communicate with motor encoders to get its rotation reading. After getting the reading, it gives the message to the rover status queue. And at the same time, it gives the same data to the MQTT queue. Then the MQTT thread will publish this to the topic. Then after getting the status message for the PID and the encoder message, it will do the calculation, then generate a adjustment message, the PID message, to the rover control queue. Then the rover control thread will read this PID message, then adjust motors. If the adjustment says set the motor to 0, it means we have already arrived at the destination, so it will publish a message says the rover has arrived to the MQTT. Then MQTT thread will publish this message to the topic. The navigation system will receive this message and give another command.
To make our data both send and receive readable and in the same format, we need to use JSON format. To parse our data to JSON, we use Jasmine, a very light JSON format parser. It's only a header file and just a few functions can do the job.
Here are the constraints that we had while working on the project. The first one is the robotic arm. The first arm we were trying to use has no encoder for the motors, so there's no data feedback and we cannot make sure the accuracy is good enough. Then we use another arm whose motor was controlled by PWM, then we can operate it accurately. And we use the same kind of motor on the arm for the rover dropping system. But this motor needs an accessory power supply. It cannot be powered by the TI board. So we have to get another power supply to connect it to the rover. Luckily, the rover's battery is powerful enough. And the third thing we have is the camera attaching method. Camera is very small. At first, we were trying to use tape, but tape is not a very stable way to do so. And since the arm will move, the camera will vibrate. So we end up using a mounting putty that is both sticky and steady.
The design is reliable in the fact that it runs for one game session as intended. The blocks are consistently picked up by the robotic arm and placed in the rover drops off the blocks correctly, and the game states don't get stuck during the run. However, there are aspects of the design which are certainly unreliable. The encoders in the rover wheels do not perfectly measure the position. Small enough rotations are impossible to detect, which causes errors to build up over time and messing up the rover's orientation in the grid. To account for this, we have been adjusting the rover manually back to its starting orientation when it comes back to the home position after dropping off foam blocks, which works well enough to allow the game to continue as designed. We originally planned on a 10-foot by 10-foot grid. However, with the global pandemic and being stuck in limited space apartments, we had to make do with a smaller playing field as seen in this video. To account for this, we simply do not use the edges on the GUI, which are not present in the physical playing field.
Our navigation system will stop working when receiving wrong sequence number message and will wait until you receive the correct sequence number message. Our project is based on a 10 times 10 file, so it will not work if we exceed the range. As for the camera sensor, it needs plenty of light to make data accurate. So if there's not enough light, there may be wrong data sent from camera. To solve the problem, we add a data filter to take away most of wrong data, which can make the arm work as accurate as possible.